Hello, everyone. We are going to consider a couple of examples from our book. Hello, everyone. We are going to consider a couple of examples from our book. We're going to start with example 2, and example 2 is about Airy's equation. This equation is important in optics. It's a second-order equation. Second derivative of y minus x, y equals 0, and again important in optics. And equation has no singular points. Which is good for us, right? Good for us. So we are going to look for a serious solution about x equals 0. Well, just standard series, standard power series about 0. Very easy, right? The coefficient x to the power of n, not x minus something to the power of n, but just x to the power of n starts with 0, ends at infinity, and we are going to differentiate it right away and get the derivative n a n x to the power of n minus 1 and goes from 1 to infinity. Remember that the constant is going to give us 0 when you differentiate it, and the second derivative is going to shift the start of the series even further, n equals 2. And here n minus 1. Again, we are shifting the index because first term disappears because it's a constant. When you differentiate it, it's going to give us 0. And if we do formal substitution, it's going to give us a very, very bad series. So what I'm going to do, guys, I'm going to shift the index for my second derivative right away because I'm planning to use it. I don't have a first derivative in my equation, so I don't really worry what is the index of the first derivative. But the second derivative, there is a second derivative in my equation. I want to have it starting with 0 because I'm planning to plug everything into my equation. Well, we remember that you kind of make formal substitution. M equals n minus 1, from where n equals m plus 1, plus 2, sorry. And then when you do substitution of m, then you rename it n again and kind of get everything in terms of like n plus 2 actually. Sorry. So I'm going to put instead of n plus 2, and instead of n minus 1, n plus 1, right? 1 unit less, and a n plus 2, and x to the power of n because it was n minus 2, right? So now I'm going to put it into differential equation. And I'm going to get two terms, right? The first term is second derivative, n plus 2, n plus 1, a n plus 2, x to the power of n starts with 0, goes to infinity, minus x, which sits over here in front of y, and then a standard power series, which I copy from over here. A n x to the power of n goes from 0 to infinity equals to 0. Now what I'm going to do, guys, I'm going to bring this x inside, and it's going to shift my index over here, like from n to n plus 1. For the first series, for this one, I want to separate the first term. The first term, n equals 0. And for the second, I'm going to bring n in. Well, I don't want to kind of shift the index one more time. So I won't have all indexes starting with the same point. So if I separate here first term, I'm going to get what? When I plug in n equals 0 here, I'm going to get what? 0 plus 2 is 2. 0 plus 1 is 1, and a 0 plus 2 is a2, and x to the power of 0 is just 1, right? Well, I'm going to formally write it down. And then I write down the rest of the series starting n equals 1 to infinity. And that's going to be again n plus 2, n plus 1, and a n plus 2xn. What I did, I just took the first term of this series out. Again, why? Because this series, after I bring x inside, is going to have n plus 1 over here. And if I want to have x to the power of n to combine it with this one, I need to shift the index again. That's what I'm going to have. Well, let me first write it down how it's going to look. It's going to look like this. An x n plus 1, n goes from 0 to infinity. And I'll need to shift the index here to get x to the power of n because I'm planning to combine it to this x to the power of n. So I'll need to write it down n plus 1 x to the power of n, and starts with 1 goes to infinity. Sorry, not plus 1, minus 1 actually. Minus 1. Well, now if I plug in n equals 1 here, I'm going to get 1 minus 1, 0, which is going to give me the first term. If I plug in 1 here, it's going to give me 1, and that's supposed to be 1, and everything is going to fit. So now I have it starting both series with the same index. Now I can combine these two series. Sometimes it's going to be tricky to deal with, like, summing up two series. So I'm still keeping my first term outside. So 2 by 1 is 2, and a2 is going to be give me 2a2. Here, I'm going to have one big series with combination of coefficients. So I have n plus 2, n plus 1, a n plus 2 minus a n minus 1. A little bit complicated, right? But then x to the power of n equals to 0, n goes from 1 to infinity. What I see, guys, I see again polynomial equals to 0 for all x, which means that the coefficient must be equal to 0. And this one must be equal to 0 too, because if it's not equal to 0, then that the sum is not going to be equal to 0 either. Okay? So, well, I'm going to start calculating the terms. I'm going to scroll a little bit up. Maybe change the color. Let me choose the green. So the first conclusion is that a2 equals 0, right? And equation for the occurrence formula is going to be what? N plus 2, n plus 1, an plus 2 equals an minus 1, from where an plus 2 equals an minus 1 divided over n plus 2, n plus 1. Okay, good. We got the formula. Occurrence for, not formula, I guess. Okay, now I'm just going to calculate first few terms, like first few terms, okay? So n equals 1 is going to give me a3 equals n equals 1, a3, right? 1 plus 2 is 3. 1 minus 1 is 0, so it's a0 divided, and it's 2 and 1. I don't know oh, sorry, it's 3 and 2, because n equals 1, right? 1 plus 2 is 3, and that's 2 here. Okay, I don't know a0 yet, so I'm just going to keep a0, okay? N equals 2 is going to give me a4, which is going to be a1 over 4 by 3, right? And n equals 3 is going to give me a5. Again, I'm not going to do lots of them, but just first few so you can see the pattern. And again, the pattern is not going to be the regular pattern we already have seen. That's 5 and 4, right? But we do know that a2 equals to 0, so actually it's going to be equal to 0. I'm going to put it in parentheses, a2 equals to 0. Okay, and n equals 4 is going to be a6, which is going to be a3 over 6 by 5, but we already know a3 is a0 over 3 and 2, so we're going to have a0, 6, 5, 3, 2. Looks like we're missing 4 here, right? Interesting. One last one, okay? And again, that's just example of how differently can look the series. By the way, there is no function which is describing this series like exponential. That's just a series by itself as a function. So A4 divided over 7 by 6. And because we already know A4, it's A1, 4, and 3, we are going to have A1, 7, 6, 4, and 3. Looks like 5 is missing, right? Now I'm going to write down all the terms and then separate terms with A0 and terms with A1. Let me take a different color. So what are terms with A0? This one has A0 and this one has A0, right? So I'm going to write down that y equals A0. Well, maybe I should write down the series first. That's going to be too complicated if I start doing it right away. I'm going to write down y equals what? A0 plus A1x plus A2x squared plus A3x cubed. I'm writing down this representation, like instead of sigma notation using expansion. Well, because I'll need to plug in the coefficients. Okay, give me a second. So I'm going to do A4, a to the power of 4, A5, x to the power of 5, and so on. We don't know more coefficients now. A0 instead of A1. What is my A1? Where is my A1? I don't have any A1 actually, so I'm going to keep A1 as my arbitrary constant. I don't have any condition on A1, right? But I do know A2. A2 equals to 0. And I do know A3. A3 is A0 over 3 to x cubed. And I know A4, it's A1 over 4 and 3x to the power of 4. And I know that A5 is actually 0 again. And by the way, I know A6 actually, so I'm going to put A6. A6 is A0 by 6, 5, 3, 2 by x to the power of 6, and I do know one more. A1 over 7, 6, 4, 3, x to the power of 7, and then other terms. Now, guys, I'm going to unify terms with A0 separately and terms with A1 separately. So here is 1. A0 is going to give me x cubed over 3 by 2 plus A0 here, x to the power of 6, 5, 3, 2. I'm putting A0 outside of parentheses. And I don't have any more A0s here, but of course there are more of them where we have these 3 dots. Plus A1, and we have x plus, this one is missing. This one is A0. This one is x to the power of 4, 4, 3, plus A1 x to the power of 7, 7, 6, 4, and 3. My 7 doesn't look very nice, actually. And of course, some other terms. Okay, so we have 2 different solutions, right? This solution has powers of 1, 3, 6, and you kind of expect what is going to be next power, maybe 9, right? This solution has 1, the power here is 0, 3, 6, and this one is 1, 4, 7. Looks like they kind of jumping or adding the next, like, to next power, like 3. So next power here is going to be 10, right? And we have like terms here missing some numbers, right? So it's 7, 6, and 5 is missing, 4, 3, and for the next one is going to be probably 10, 9, and then 8 is going to be missing, then 7, 6, and then 4, 3. Well, we see the pattern, right? This first one is going to be my y1, my first solution, and the second one, okay, equation of second order, right? A second solution. I'm going to kind of write them down separately. Y1 equals 1 plus x cubed 3, 2 plus x to the power of 6, 6, 5, 3, 2 plus some other terms, and y2, it's x. Well, again, these 2 series are called Aries functions, and they are not really functions. They are actually just series. And I was telling you that lots of solutions are just series, and they don't have any like representing them functions. Okay, very good. So we are done with example 2. And I think we can move to example 3. Let me scroll up a little bit. One more example. Here is equation about a different points. So we are going to have powers of different series. Example 3. Here is same equation. Sorry. In powers x minus 1. You see, before we had powers of x, now we have powers of x minus 1. The equation is same. I'm going to just copy the equation. Second derivative of y minus x, y equals 0. But solution is going to be different. And again, that's our choice how we search for a solution. And usually it's like dictated by convenience, where actually around which x you are searching for a solution. Well, again, solution about centered about different points are going to work better around these points. And usually that's a major goal of using actually these solutions. Normally, you can use the first solution, which is about x equals 0, but it's going to take more terms to approximate the function solution if you need it. Normally, you don't consider all infinitely many terms, right? Normally, you truncate a series like at term number 2 or number 3 or number 10. So closer to the point you are, less terms you will need. Let's say maybe if you consider point x equals 1, you will need like 2-3 terms. If you use a previous solution, you will probably need 10-15 terms. So sometimes it's not big difference, sometimes it is. So I'm going to kind of deal with all the derivatives again. So my series is going to have the first derivative, and that's going to, everything is going to be same, except, well, instead of x, we are going to have x minus 1, and the second derivative is going to be n equals 2 to infinity a n minus 1, x minus 1 to the power of n minus 2. I think everyone understands how to shift the index, right? And I'm going to shift the index a little bit for this one, for the last one, just to have it starting with 0. So n 0 to infinity a n plus 2 n plus 2 n plus 1 x minus 1 to the power of n. Okay, I'm going to plug in everything into my equation, and I'm going to have n equals 0 to infinity n plus 2 n plus 2 n plus 1 x minus 1 to the power of n. That's my first term. For the second term, remember I have x in front, right? So I have actually minus x in the series an x to the power of n. Sorry, not x to the power of n, x to the power of minus 1 to the power of n, and goes from 0 to infinity. A little bit weird that x is not x minus 1, right? We cannot bring x here, or we can actually, but it's not going to give us anything nice. So what I'm going to do, guys, let me change the color. I'm going to represent this x as x minus 1 plus 1. It's still same x, right? But I'm going to have the parenthesis x minus 1. And I'm going to have 1 without like x minus 1. But let's see how it's going to look. So right now I'm just working with the second term. So I have sigma an x minus 1 to the power of n plus 1. I'm bringing this x minus 1 in. And I'm going to have just 1 multiplied by this function, and that's going to be an x minus 1 to the power of n. Starts with 0 to infinity, and again n starts with 0 to infinity. So I'm going to get two series. Again, let me change the color. I took this one and multiply them separately by this series. And got two series separately. Yeah, so I'm gonna make our life easier. So I'm just going to combine everything together. Let me get back to my red color. Sorry. Yeah, guys, I was thinking to maybe I don't need to write down it as one big series. I'm just going to collect the coefficients, and that's going to be a little bit maybe easier. So what I'm going to do, guys, I'm going to literally consider the powers of x minus 1 like this. X minus 1 to the power of 0, x minus 1 to the power of 1, x minus 1 to the power of 2, and collect coefficients in front of them. Because you see, 3 series, starting shifting the indexes is going to give me nightmares. So, and this is a good way to do this when you have complicated expression. It's actually easiest way to do it. So what is the coefficient of x minus 1 to the power of 0? Well, here if we plug in n equals 0, we are going to have a2, right, and then 2, 1, and kind of, are we going to have anything from this one? If we plug in n equals 0 here, we are going to have the power 1. So this parenthesis or this sigma is not going to produce anything into here. This one, if it's n equals 0, we are going to have a 0. So minus a 0. Why do I have minus? Because I had minus in front of the whole expression, right? It's equals 0, and I can solve it. I can write down that a2 equals a0 over 2 multiplied by 1. Nice, right? You can write down divided by 2 if you wish. Now, the first power, x minus 1 to the power of 1. Well, this one is going to give me a3 by 3 by 2, right? This one is going to produce 1. This one actually, the green one is going to produce 1, right? If you plug in 1 here, it's 1. If you plug in 0, n equals 0 here, you are going to get power of 1 here. So it's a0. And the last one is going to produce, sorry, n equals 1. 1 here, it's going to be minus a1. Looks a little bit crazy, but I'm going to solve it for a2, right? a3, sorry. That's a1 plus a0 divided by 3 by 2. But I already know a0. Oh, a1. No, I don't know a1 actually. Just I have only these two coefficients. Okay. I think move on to the next one. I'm not gonna do too many of them. So just like 2 more, okay? a4 by 4 by 3 minus, next one here is a1. Next one here is a2 equals 0. I'm going to get a4 equals a1 plus a2 divided by 4 by 3. Well, here I do know something. I do know a2, so I'm going to plug it in. a1 plus a0 over 2. I'm writing down 2 multiplied by 1 is 2 by 4 by 3. I don't know, I'll bring it to common denominator, okay? Over here, that's 2a1 plus a0, and here 4, 3, 2. Well, I'm not super creative. I'm going to do just one more. Sorry, guys. Let me stop it for a second. Sorry for the interruption. We're going to continue, and that's going to be our last coefficient. So a5 by 5 multiplied by 4. I'm going to scroll a little bit up. Minus a2 minus a3 equals 0, and we are going to have a5 equals a2 plus a3 divided by 5 multiplied by 4, and we do know some coefficients already. We know a2 and both a3, so I'm going to write down a2 first. That's a0 over 2, and then a3, which is a1 plus a0 divided over 3 multiplied by 2. This multiply does not like that multiply. And divided by 5 and by 4, of course. Well, I'm going to maybe simplify it a little bit. It looks like common denominator of both fractions over here is 6, so I'm going to have 3 3a0 plus a1 plus a0 and divided over 6, 5, and 4. Maybe, guys, I don't want to copy everything. I'm just going to combine a0 and this a0 together, and the 3 of them and just 1 of them. I'm just going to erase this 4 and write down. There is this 3 and write down 4. And then we don't need this. Oh, maybe I should erase the whole thing. 4a0 plus a1. Okay. Well, now it's time to probably plug everything into the series. Plug coefficients into the series. And the series is going to look like what? Y equals a0 plus a1 x minus, sorry, supposed to be 1 plus a2 x minus 1 squared and so on, right? Let me change the color. So I'm going to start over here. So a0 is just a0, right? Plus a1, I guess, is just a1. But I think a2 is already going to be expressed through a0. So I'm going to have a0 over 2 and x minus 1 squared. Yeah, I don't need the 0. I cannot erase it. That's very strange. And then we have what? a3 by x minus 1 cubed. Where is a3? a3 is this one, right? So a1 plus a0. I'm just going to divide over 6, okay? X minus 1 cube. And one more. We have like some more coefficients, right? a4 is going to be 2a1 plus a0 divided over 4, 3, 2 plus just last coefficient, but I think I have to write down here parentheses with x, and that's not going to fit here. So I'm going to move to here. So the last one is 4a0 plus a1 divided over 6, 5, and 4. I think we can just multiply all of them. And don't forget about x minus 1 to the power of what? We have 1, 2, 3, 4, and 5. And because we don't have more coefficients, we are going to put lots of dots. Now, what I'm going to do, I'm going to separate coefficients with a0 and coefficients with a1. So a0 here is 1. Here we have x minus 1 squared over 2. Come on, keeps giving me different triangles and other stuff. I think I picked something here when I was setting it up, and now it draws all the triangles for me. Next a0 is going to come from this term, the cube, right? So it's going to be x minus 1 cube over 6. And next one is going to come from the next term again. We have a0 represented in all terms, almost like the part, right? Next one is going to be x minus 1 to the power of 4. Well, let me multiply. 3 by 2 is 6, and by 4 is 24. And the last one is going to be, well, if I'm cancel this 4 and this 4, I'm going to have x minus 1 to the power of 5. And over here is going to be 30, right? 6 by 5. Well, I'm not sure 100%, so I suggest you to check me. Come on, where is my, why it's so small? I think I just touched something. Okay, I'm going to put lots of dots because there are other terms, of course, but we don't see them. And now start combining terms with a1. So we have x minus 1 to the first power. I don't know, I can write down 1, but it's not necessary, right? Next one is coming from cube, right? That's going to be x minus 1 cube over 6. Again, not triangle, over 6. Next one is going to be this one, right? And if I cancel 2 and 2, I'm going to get x minus 1 to the power of 4 divided by 12, right? Because 2 cancels and we have only like 2, 4, and 3. And plus Oh, well, at least that's going to be the last one. Plus x minus 1 to the power of 5. And I have to multiply all of this, right? 6 by 5 is 30, and by 4, it's 120. And yes, maybe some of them can be represented as factorials, but that's not the point. The point is just to see that there are two functions represented, right? You see function number one is 1, x minus 1 square, cube 4 fifth degree, and second function is 1 cube 4 fifth degree 2, but they are different just because they sometimes have different terms. They're not identical. I think we can just label them as two different functions and say a couple of words that this is y1, and I don't know how to label this one because it's kind of split into, right? I'm going to start labeling here and kind of continue over here. Why don't I label this y1 and this y2 would be like more logical, right? y2. So I'm going to write down that y equals a0 y1 plus a1 y2. How do I find this a0 and a1? Use initial value problem, which gives you y, for example, at 0. Well, in this case, I think it's going to be y at 1, not at 0, just because it's about 1. Well, I'm not going to write it down, like, because, well, I did not set it up over here. So most likely it's going to be x equals 1, actually. So maybe y of 1 equals to some number, I don't know, 3, and y prime of 1 equals some other number. And then you can kind of differentiate the series, substitute, and find the constants. That's supposed to be too difficult just because normally all terms are going to turn into 0 except maybe the first one. And when you differentiate, that's going to be, again, maybe the first one. Well, I'm going to just put some arbitrary numbers here, but again, these are initial conditions. And again, it's not necessary that the initial conditions are given at 1. They can be given at 0. It's going to make our life a little bit more complicated, but not super complicated. Okay, but normally, if you do the series about 1, initial conditions are also at 1. Okay, what I'm going to do, I think we are done with this, and I suggest you to practice solving equations. By the way, 2 words. This method where you do not combine everything under one sigma notation, it's not illegal. This is actually most typical way to find the coefficients, because sometimes combining into one sigma notation is going to give you a very long equation, plus it's not going to make your life any easier, because normally you don't need like infinitely many coefficients. And sometimes, even if you get the formula, you understand that this formula is not going to give you a general solution, like general expression. Like over here, it's really hard to get a pattern, right? It's like 6, 12, 120. So these numbers are related a little bit, but not much. So basically, maybe if you need few first terms in your series solution, like 2, 3, 4 terms, you don't need to deal a lot with this shifting indexes, writing down everything into one sigma notation. You can just check the powers of like the coefficients in front of certain powers of x. Start with 0, then go to 1, then go to 2, then go to 3. Remember that the coefficients must be combined to 0 just because it's a polynomial, but not a polynomial which you can solve for x. It's supposed to work for every x, which means that coefficients must be equal to 0. Okay, that's all for today, and sorry for interruption. Again, these initial conditions are just like, just random ones. You're supposed to kind of refer to actual initial conditions if you solve initial value problem. Okay, that's it. Thank you, and I'll see you in your next lecture. Induce